The following complex fraction, 12n squared minus 363 over 2n squared minus 21n plus 55 all over 14n squared plus 73n minus 22 over n squared minus 14n plus 45. Key thing to notice about this expression is that each denominator or numerator can be factored, and we're going to do that so we can see what factors are common between each of these fractions and then go ahead and cancel them out. Let's start off by looking at this 12n squared minus 363. I can see that both of these terms are divisible by 3, meaning that I can take out a factor of 3. You can quickly tell what large number can be divided by 3 by adding the digits, and if the sum of the digits are a multiple of 3, then this entire number is a multiple of 3. So for example, 363, 3 plus 6 is 9, 9 plus 3 is 12, 12 is divisible by 3, therefore 363 is also divisible by 3. So I take the factor of 3 out, and in this bracket I'm left with 12 over 3 is 4, and squared minus 363 over 3 is 121. I notice that 4n squared minus 121 is a difference of two squares. This is because 4n squared can be square rooted and be left with a whole number. Same case for 121, which means that we're going to be left with 3 bracket 2n plus 11 and 2n minus 11. And if you multiplied these brackets back out, you would be left with, again, 4n squared minus 121. Now we've arrived at the fully factored form of 12n squared minus 363, which is 3 bracket 2n plus 11, and then bracket again 2n minus 11. So this is how we're going to approach each of these numerators and denominators here. We're going to reduce them to prime factors and seeing what we can cancel out. Next, let's try to factor out this 2n squared minus 21n plus 55. A systematic way to do this is we can take the coefficient of the n squared, 2, multiplied by the constant, plus 55, we'll have 110. Write this here so that you remember. And then minus 21. So now we're looking for two numbers that multiply together to give me positive 110. And add together to give me minus 21. I think the numbers we're looking for are going to be minus 10 and minus 11, so I'm going to rewrite this expression a little differently to show my minus 10 and minus 11. And now you can see that these two are the same as each other. All I've done is I've separated this minus 21n into minus 10 and minus 11. And what this allows me to do is now I can factor by grouping. To factor by grouping, I'll first look at the 2n squared minus 10n, and I notice that we can take out a common term of 2n, and inside the bracket we'll be left with n minus 5. And then we look at this side, the minus 11n plus 55. I can take out a common term of minus 11. Inside this bracket I will be left with n, positive n, and negative 5, because we've taken out a negative sign out of this positive, so this becomes a negative. Factor out by grouping, what you should be left with is two identical brackets here, which means that we can get rid of one of them, and our factors are going to be 2n minus 11 and then n plus 5. These are our two factors for 2n squared minus 21n plus 55. We're looking to factorize 14n squared plus 73n minus 22. You can factorize this the same way we did the last quadratic. However, to multiply these two numbers together and then find two factors in your head, it's not going to be the most time efficient manner. So I think for this one we're going to trial and error instead, which means that we're going to, for example, the factors of positive 14n squared, they have to be either 2n and 7n, because they would multiply together to give me 14n squared, or they're going to be 1n and 14n, because that also gives me 14n squared. And that's the case for minus 22. I can either have minus 22 and positive 1. They would multiply to give me minus 22, positive 22, or minus 1. That would also give me minus 22. And then minus 11, positive 2, and then plus 11, minus 2. Now you can go ahead and play with these numbers. When I see this plus 73, I'm thinking that if I want to get to plus 73n by adding two of these numbers together, then I must have, one of them must be relatively large. For example, 7n and plus 11 would give me 77n, so that sounds plausible. So let's try 7n here, 2n here. Now I want the 7 to multiply with plus 11, so I'm going to put the plus 11 on this side because you would cross multiply over. And then this would have to be minus 2. And now you want to expand these brackets out and see if they give you the original quadratic. So for example, 7n multiplied by 2n, 14n squared, 2n minus 2 minus 4n, 7n plus 11, 77n, 77n minus 4n, 73, and then minus 2 multiplied by plus 11 is minus 22. So these are the correct factors. It's going to be the factored version of the quadratic 14n squared plus 73n minus 22. Here we're going to factorize n squared minus 14n plus 45. Relatively easier compared to the last two which we have just factorized. We're looking for two numbers that multiply to give positive 45 and add to give minus 14. And the coefficient in front of n squared is going to be 1, so we know that the first terms must be 1n on each of the bracket. So I think they're going to be minus 9 and minus 5. N times n is n squared. Minus 9n minus 5n is minus 14n. Minus 9 times minus 5 is plus 45. And this is the factored version of the quadratic. Factored completely each of the polynomials in my complex fraction. I can now rewrite this complex fraction with the factors that we know.